Let's get started. So, we've recently started talking about quantum cryptography, and here the goal is to use the unique properties of quantum information in computation to do more than what we can do in classical cryptography, right. So, last time as you recollect we saw key agreement, and we have also studied the quantum one time pad. And now naturally the logical next question is how to do encryption, and in particular I promised to show you at least one advanced application. So, the goal for the last remaining classes that we have is to look at quantum public key encryption and how to generalize that to fully homomorphic encryption. Okay. So, we will start discussing that today. So, first let's jump right into quantum public key encryption. Okay. And last time we ended the discussion with this question, right, that if I want to encrypt an arbitrary mixed state, then how should I proceed? So far we have seen how to do a quantum one time pad, right, and we showed that this was perfectly secure. Okay. Now, I want to generalize that to public key encryption. So, are there any thoughts or ideas on how I might proceed to do such a thing? And the hint that I have is that we will directly use the ideas from the quantum one time pad. So, maybe it's good to quickly recollect what we were doing for the quantum one time pad. Okay. So, for the QOTP, so if I had some arbitrary mixed state rho. So, as he says, what we were doing in order to encode this arbitrary mixed state into a state that reveals no information is that we were applying some x to the a, z to the b, right. And here a and b are random classical bits. Do you all remember this? So, we did a proof as to why this was a quantum one time pad. We did this last time. And now my question is how do I generalize this to a public key encryption scheme? So, in a public key encryption scheme, what do I need? Well, I need a public and a secret key, and I need to be able to sort of create a ciphertext that hides my state. So, again let us think of the state as rho. Okay. Now, how should I use this QOTP idea to get something much more powerful like public key encryption? The idea is actually very simple. All right. So, in the interest of time, let me not wait for an answer. So, what I will do is I will actually use classical public key encryption to help me. Okay. So, note that we have already seen classical public key encryption schemes that are quantum secure, or at least conjectured quantum secure, right, like the lattice based PKE scheme that we saw. So, what I want to do now is I want to use a quantum safe public key encryption scheme together with a quantum OTP, right, and I want to build this QKeygen, QEnc and QDEC. So, now can you tell me how should I build these algorithms? So, as usual this keygen will take the security parameter, okay, and enc will take some arbitrary mixed state rho, okay, together with a public key, and DEC will take the secret key and some ciphertext. Right. Okay. So, I gave you all the information you need. I am going to use the quantum one time pad, and I am going to use a quantum secure classical PKE. Okay, what's the issue with a quantum one time pad? So, a quantum one time pad is giving me something really nice, right? It's allowing me to take an arbitrary mixed state and erase all the information about the state, right, in an information theoretic way, such that it can nevertheless be reversed if I know the secret. So, my secrets are these classical bits A and B, okay, and I know how to do this one time security. So, what is the issue if I just use a QOTP many times? So, I mean there are actually multiple issues. I guess one of them of course is that in a public key encryption scheme A and B will not be even known. I mean the encryptor does not know any secret. So, of course, that is an issue. And I mean if I wanted to go even slower, I could go via a private key encryption scheme. But let's jump to public key encryption, right. So, assuming that this question of knowing A and B is not an issue, what is the security issue?
One time can only be used once.
Exactly, just as the name suggests, a one time pad can only be used once, right. So, if I give you multiple encryptions with A and B, then that leads to a security break, and this exactly leads you to the solution. So, what should I do to fix it? Yes.
Maybe you can apply the one time pad multiple.
Very good. So, apply the one time pad many times. What does that mean? With different secrets, right. So, because using the same secret many times is insecure, obviously the sort of logical thing then to try is to use different secrets at for different ciphertexts. So, that would be fantastic. So, here is what I could do, right. I could pick A and B at random, right, perform QOTP with A, B and row. So, I will just define this as QOTP A, B row, okay. Okay, great. Okay, so, if I just do this much, is it enough? Even decryption is not clear here, right. How will I even decrypt? So, in the OTP case to decrypt I need A and B, and here if the encryptor is picking A and B at random, then obviously the decryptor cannot decrypt, therefore. Exactly. So, encrypt A and B using classical PKE, right, that is the obvious thing to do. So, let us just do that. Okay. So, what okay good. So, now tell me what is my key generation process. Exactly, same as the classical. So, if I say if I let pi be a classical Q secure PKE, right, then my keygen should just be pi dot keygen, right, and this will output some PKSK, and I output the same PKSK, right. And now how do I decrypt? Okay, so, this OTP part I am calling it some row prime, and I will just call this pi dot CT, okay, to illustrate that this is just a classical ciphertext. So, now what should I do? Well, obviously I would decrypt pi dot CT using pi dot SK, right. This gives us AB, and then recover row using QOTP decryption, right. So, is the correctness clear to everybody? So, we have just used two very simple building blocks, the quantum one time pad which we talked about last time, right, and the just you know, quantum secure classical PKE. And see, all of this, that I mean it is very natural if you think about it. So, look, we already have a classical PKE which we conjecture quantum secure. What does that mean? That if I want to only encrypt classical information, then this PKE suffices. But the whole point that we are the whole goal that we are trying to achieve right now is that we want to generalize to encrypting quantum things, right, quantum states. We do not want to just encrypt classical states, we want to encrypt quantum states. So, now we are using the fact that the QOTP, the secret key is actually classical bits, right. So, we could encrypt that using a classical scheme, right, and the QOTP can hide quantum information. So, we will use that to hide the quantum information. So, it is a two step process, and the secret key of the QOTP we will hide using a classical PKE. Okay. So, it is a very natural scheme. So, correctness is, you know, obvious, it just follows from correctness of QOTP and pi. Correctness follows from that of QOTP and pi. Remember that pi is the classical PKE. But you know, we have to as usual be very careful about security. So, what does security here mean? So, remember the indistinguishability game. Okay. So, the adversary will get the public key, the adversary will output two messages, in this case it will be two quantum states, let us say, you know, rho 0 and rho 1, and it will see a ciphertext of one of them and it needs to guess which of the two it saw. So, now how should I argue security? Security very intuitively will obviously build upon the security of the OTP and the PKE, right, that, well, those are the only two things we used. So, obviously security will rely on that, but I need to do the argument carefully, right. So, I want CT of rho 0 to be indistinguishable from CT of rho 1. How should I proceed? Okay. So, as usual, let us try to go step by step. So, the first step which we call hybrid 0, this is where, you know, the adversary sees PK and CT of rho 0, right, and I want to get to some hybrid whatever, okay, where the adversary sees PK and CT of rho 1, and I want to kind of change the distributions, you know, little by little, so that I can argue that subsequent distributions are indistinguishable, and as long as I do not do too many of these changes, then the first and the last distribution can be argued to be indistinguishable, which is what I am hoping for. Okay. So, how will I do this transition? So, what should hybrid 1 be? Anyone? Okay, very good. So, so yes, what he suggested is correct. So, let us again give ourselves some notation. So, this CT is, you know, some QOTP ciphertext, I think I already gave it this notation rho prime, and some pi dot CT, right. So, pi dot CT AB, right. So, this was our notation. So, as he suggested, the next step could be that, you know, you change pi CT to encrypt 0 0 instead of AB. And why should this be okay? Just from the security of the public key encryption scheme. Okay. Why can't I do it the other way around? So, what he suggested is that in my first step, instead of changing you know, rho prime to encrypt rho 1 instead of rho 0, I am first changing the ciphertext to encrypt 0 0 instead of AB, This is his suggestion. Why cannot I do it in the reverse direction? I mean, why can't I instead of instead of working on this part first, why can't I work on this part? So, rho prime is an QOTP of rho 0. Why can't I change that directly to be a QOTP of rho 1? The answer that was given is that I am given an OTP of some rho 0, and since it is perfectly secure, the only way I can recover rho 0 and replace it is by decrypting it. But no, that is not correct. In fact, as the adversary I will never be able to decrypt it. So, that strategy would not work anyway, right. And moreover, if that were my goal, then I could just throw away this rho prime and compute a new rho prime, right, with some other a prime b prime. And so what if the two are inconsistent? So what if I have encryption of rho 1 using a prime b prime and ciphertext for some a b. Note that the adversary in general cannot decrypt anything, right. So, if the OTP is encrypting something else and the ciphertext is encrypting something else, it is not that the adversary can really distinguish, but I claim that I still cannot do that. And why is that? That is exactly right. So, it is because I have to worry about the distributions of things. Okay. So, rho prime depends on AB. So, I cannot get rid of the dependency from AB. If I simply throw away rho prime and compute a rho double prime with something else, right, this new rho double prime, which is now encrypting rho 1, is not distributed correctly with the second component of the ciphertext. So, these two components in the ciphertext, right, the QOTP and the classical ciphertext, these are they are correlated because they share AB. So, you cannot, if you simply throw away one and replace it with another, right, then you need a very careful argument to say that the distribution does not change. So, then let me ask you, why does his other suggestion work? So, he is saying that I could instead just replace the PKE ciphertext from AB to something else. So, I said let us just do 0 0, I mean that is as good as anything else. I could do 1 1, it does not really matter. So, then why is not it a problem? Okay, the answer was that it is okay to do this because we do not know what rho 0 is. So, we only know, okay. So, by the way, I mean rho 0 and rho 1 both are known to the adversary. So, in the security game, the adversary, I mean since we have spent time on these security definitions before, I did not want to spend too much time on it in class again, but remember that this is the game. There is a challenger and an adversary, right. The challenger gives the public key, the adversary gives rho 0, rho 1, and the challenger gives enc of rho sub b, where b is a random bit. Okay, and then the adversary outputs a guess for b. So, what you are saying also does not work. And actually the reason that I can go from hybrid 0 to hybrid 1, it is not totally obvious, it actually needs a proof. So, the reason it is true what your classmate said, that I can go from hybrid 0 to hybrid 1, which is that I can change the bits in the PKE ciphertext, the classical ciphertext. This is true, but this actually requires a reduction. So, I need to do a reduction where I have the PKE challenger, okay, I have a PKE adversary, okay, and I have my Q PKE adversary here. So, I need to do a reduction which says that if there exists a Q PKE adversary who can distinguish between hybrid 0 and hybrid 1. Then there exists a a PKE adversary, let us call this B, let us call this A. Okay. I need to argue that if there exists an A, then there exists a B who will break the security of the PKE scheme. I need to argue this, and how does this work, this reduction? Okay. So, let us sketch it at a high level. So, the PKE challenger will give the pi dot pk. Okay. Our guy here, our reduction B can simply forward this as the q pke pk, simply forward it, because our scheme has the same public key and secret key as the underlying public and secret key. Okay. Now, this adversary gives pi 0, not pi 0, I am sorry, rho 0 and rho 1. Yeah. So, this guy gives the challenge as rho 0, rho 1. Now, what does our reduction do? So, now I want to compute a QOTP of which of the two? So, let us make sure that we are sort of really getting this, right. So, what is our goal? Our goal here is to argue that hybrid 0 and hybrid 1 are indistinguishable if pi is secure, and by secure I mean classically secure, right, because pi is a classical scheme. So, now tell me what should B compute the QOTP of. So, remember what is hybrid 0 and what is hybrid 1. Hybrid 0 is let us be very explicit. So, what is rho prime? It is QOTP of rho 0, okay, and pi dot Ct of A comma B. This is our ciphertext in hybrid 0. In hybrid 1, I am claiming that I simply change what is sitting inside pi, the ciphertext of pi. So, what is my my quantum ciphertext in hybrid 1? Good. So, rho prime, which is what? QOTP of rho 0, very good, and pi dot Ct 0 0. This is what I said I am changing. So, now go back to my reduction. Now, tell me what am I computing a QOTP of? Rho 0, yes. So, because I am distinguishing between hybrid 0 and hybrid 1, and in both of them the OTP part is actually the same, is it not? So, I have to do the same, the OTP will be of rho 0. But now I need to play with my PKE challenger, right. I need to play the security game with the classical PKE challenger. So, I am supposed to give this challenger 2 messages. It is going to be AB or 0 0. Basically, in hybrid 0 I am using a random AB, right, and in hybrid 1 I am using 0 0. So, my challenge to the PKE challenger is AB comma 0 0. So, now I will get a pi dot Ct, okay, of one of the two, right, either AB or 0 0, and now let me give this some name. So, let us call this M0, let us call this M1. So, I am getting a pi dot Ct of MB, and now the reduction B need to return the QOTP to the QPKE adversary. So, what should I give A now? Rho prime and pi dot Ct MB, isn't it? And now my A is supposed to break security. So, it will guess B prime, right. It will try to I mean it will guess B, I will call that guess as B prime. Okay. So, now if note that if I am in hybrid 0, right, then I get to see an encryption of AB. If I am in hybrid 1, I get to see an encryption of 0 0, right. So, I gave my QPKE adversary A exactly the distribution of either hybrid 0 or hybrid 1, right, and I am asking it to distinguish between hybrid 0 and hybrid 1. So, if it can figure out what the bit is, this B, what it is, then the reduction can also figure out what is the message inside the pi that I received. So, it is only because of the existence of this reduction that I can claim that hybrid 0 and hybrid 1 are indistinguishable. Okay. It is because I can generate the other parts of the distribution simply by using what the PKE challenger is giving me. Is it fine? So, therefore, hybrid 0 and hybrid 1 are indistinguishable. So, now what should I do? Now, I have changed my PKE ciphertext to be 0 0. So, now what should I do? Now, I can replace the quantum state. Which means that instead of row 0, I swap it out and make it row 1. Okay, and at this juncture I can do this because there is no longer any dependence between the QOTP and the pi ciphertext. Okay, and now in the next hybrid, so actually this can be my final hybrid, right. So, now I can just go directly to hybrid 3. So, here I can replace pi CT with AB again, right, and this is the correct ciphertext for row 1. Yeah, that is what good. So, he is asking whether so he is commenting that because pi is a secure encryption scheme, you cannot distinguish between the encryption of AB and 0 0. Yes, that is what we were using in our reduction, but I would like everyone to spend a little bit of time on this, maybe offline, where you really understand why the sequence of steps is what it is. So, even when I replace the encryption of AB to 0 0, I am sort of changing the distribution, right. I mean, now my pi encryption is no longer encrypting the AB that are sitting inside the QOTP. I am changing the distribution, and of course, I need to change the distribution because I need to get to the final hybrid where I have an encryption of row 1, right. But why was it okay for me to do it? Because I was able to do this reduction, which says that I can use the security of PKE, right. I can play with the PKE challenger, and whatever the PKE challenger gives me, either an encryption of AB or an encryption of 0 0, I can use them to now generate a ciphertext for either in hybrid 0 or in hybrid 1. So, the reason I could do this was that I was able to sort of argue that anybody who distinguishes between hybrid 0 and hybrid 1 can be used to break the security of pi. I was able to prove this. Okay, let me repeat that because it is important. I was able to prove that anybody who can distinguish between hybrid 0 and hybrid 1 can be used to break the security of pi. Therefore, it is okay for me to go from hybrid 0 to hybrid 1 under the assumption that pi is secure. Does everyone get that? Okay, so the sequence is important. Now, once I broke this dependence between the OTP part and the PKE part, right, after that I can play with the OTP part. Previously I could not, because this correlation was there and I was not going to be able to make any argument about the distribution. Like on what basis can I say that these two hybrids are indistinguishable, right? But once having broken the connection between the OTP part and the PKE part, now I can in fact sort of leverage the security of OTP and switch that around. No, my friend, not at all. So, the question is, can we say that the pi CT is like a signature for
like the cipher, like whenever you include the quantum one-time pad.
For the OTP? No, we cannot say that. So, I mean I am saying this somewhat strongly because I mean I am saying the no, we cannot somewhat strongly because you know using these terms in cryptography carefully is very important. So, a signature is something completely different, right. It has its own definition, it has its own correctness, it has its own security properties. We cannot we should not mix these things. So, it is in no way is it like a signature. I think maybe intuitively what you are trying to say is that you know somehow, at least this is what I can intuit from your comment, that maybe you are saying that you know in some sense like a signature is binding to a message and you want to break that correlation. Yeah, but no, a signature is that it is a you know it is binding to a message, but it is something much more and different. So, here indeed you want to break the correlation, but there is no notion of signature over here. Okay, good, but I mean the intuition was right, but yeah, the answer is that be very careful in using these crypto terms, because you know they have extremely precise meanings. So, if we play with them, then we are likely to make a little bit of mess. So, that is why we did this reduction, right. So, now we can see that why are hybrid 0 and hybrid 1 indistinguishable, because we assume pi is secure, and if there exists an attacker who can distinguish between hybrid 0 and hybrid 1, then I can build another attacker called B over here who can break the security of pi. Okay. So, this is why hybrid 0 and hybrid 1 are indistinguishable, and then having replaced the ciphertext pi, the pi ciphertext, right, from AB to 00, I broke the dependence between the two, right. So, for example, if this had been a signature, at this point I would be dead. You see, so it would have not worked had it been a signature, because if it had been a signature, then there is an efficient way to verify the correlation, and when I break the correlation, then the verification no longer works and you know everything falls apart. But because luckily it is not a signature, I can argue that breaking the correlation did not affect me, so long as pi was secure. Yeah, and having broken the correlation, I can replace the quantum one time pad, okay, because again I can generate the rest of the distribution independently. The distribution includes what? The QOTP and the pi CT, right. Now, I can simply generate the pi CT on my own independently of the QOTP, right. So, that means that I can simply generate PKE ciphertext of 00 on my own, and I can replace this this QOTP with row 1. Okay, and then having done that, I can go back to encrypting AB. Very good. So, very good questions. So, that's you know that's our PKE scheme. Okay. So, it is a simple nice combination of QOTP and classical PKE.